Hello and welcome back to another LeetCode video. Today we're going to be doing the hard problem from today's biweekly contest. Honestly, it's definitely not easy, but it's a little bit easier than the previous ones we've done. But let's get into it. So it's find a good subset of the matrix. You're given a matrix m by n, and it says let's call a non-empty subset of rows good if the sum of each column of the subset is at most half the length of the subset. And so they're giving you this example, return an integer array that contains row indices of a good subset sorted in ascending order. If there are multiple good subsets, you can return any of them. And if there are none, return an empty array. Subset is a subset is some rows that can be obtained by deleting some or none or all rows from the grid. Okay, so let's start with this example one, and let's see what they mean. So for first one, we have 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 1. And so what they mean is you want to get some rows, and this can be any amount, one or more, where if you look down the column of the rows you pick, the number of ones is half or less than the number of rows. So for example, if this is row 0, row 1, row 2, if we pick these two rows right here, row 0 and row 1, then if we look down the columns, we can see, so this has 0 ones, this has 1 ones, this has 1 ones, and this has 1 1. So this is a valid solution because we have two rows. So we need the number of ones in each column to be half or less. So half would be 1 or less. And then we don't want to use, so intuitively also, you want to think about like what kind of rows you'd want. Well, you don't really want rows with all ones, like those would be bad rows. But any solution is possible, so we don't need all the combinations of rows. We just need one solution. And so let's think of some simple solutions. So what's a simple solution? A simple solution would actually be, the simplest solution would be if the whole row is zeros, because now the length of our subset is 1, and every column is 0 ones. So that would be like the simplest solution you can have. Okay, and now let's look at example 2. So this is kind of what they're saying, where you have grid 0 and they chose the 1. Now let's look at example 3. And so you have 1, 1, 1, 1, 1, 1. And so you can't pick anything here because no matter what you pick, your number of ones will be more than half of the length of the subset, right? If you pick one row, then it would need to be floor. So it would need to be 0 ones, which would be, wouldn't work because they're all 1. And if you pick 2, then you would need to have 1 ones and you'd have 2. So this one wouldn't work. So let's actually go down from the simplest solution to a more complicated solution. So let's actually delete all this. And now that we know that the simplest solution, I'm just going to draw a matrix. Let's say we draw a 4 by 4. We can even draw a 5 by 5. Or yeah, let's draw a 5 by 4. That'll make it easier. And I'll show you why. So 3, 4. We'll just have 4 rows. Okay. So the simple solution, like I said, is this, where you have one row where all of the numbers in the entire row are zeros, and that would be a length 1 subset. Now let's think about how we can get length 2 subsets. So length 2 subsets means we have 2 rows, and the ones in each column have to equal the length of the subset divided by 2, right? So it would have to be 1. And so that would be something like this, right? So you'd have to have 2 rows where for every single column, there have to be at most 1 1. And so it can either be 1 0 0 1 0 0, but it can't be 1 1. So at no point can there be 1 1. So that's going to be our 2-row solution. Now let's think of a 3-row solution, and let's ask ourselves, do we ever want a 3-row solution? So what would a 3-row solution mean? Right? So if there's 2 rows, so rows equals 2. Let's just make this bigger. So if rows equals 2, then we can have 1 1 in every column maximum, right? Because it's the length of the subset over 2. So it would be 2 over 2 equals 1. Now, what about if we had 3 rows? How many ones could we have? So for 3 rows, it would be 3 over 2. And then they want you to round up here, actually. So you could see that the length of each column should be at most floor over 2, which means floor of this is 1. So you're only allowed to have 1, 1. Well, if you can have a 3-row subset, right? Let's say you have some 3-row subset, whatever. Think about it. You can only have 1, 1 in all 3 of these columns. So if you can only have 1, 1 in all 3 of these columns, well, wouldn't you always have a row equals 2 solution for that, right? Because if the most you can have is 1, and for 2 you can have 1, why would you want to add another row? It doesn't make any sense, right? Like, you're just adding a row for no reason, and your maximum number of ones you can have is still the same amount. Like, we could have 1, and now we could still only have 1. So for this solution, in order for this to be a solution, it would have to be something like this. But this is also a solution then, so there's no reason to have that. So we can realize from this that we don't ever really want an odd number of rows, right? So we don't want r equals 3, r equals 5, because we're not getting anything by getting an odd number of rows. Like if 5 is a solution, then we would also have a 4 solution, right? Because a 4 solution would have to have the same number of ones as a 5 with just one less row, which is a benefit, right? We want as little rows as possible, and we want to be able to have as many ones as possible. So if you can have the same number of ones, but you can have less rows, that's better for you, right? Because a row can only be zeros and ones, so it's guaranteed to be at least as good, if not better, solution. So that's one thing we know. So we can quickly eliminate these like 5, 3. Okay, so a good solution would be row equals 0, or this would actually be 1 row, right? 2 rows. We don't want 3. What about 4? So for 4, let's actually look at this. Let's redraw this again, and let's do the same thing. So we're going to draw a 5 by 4. Yeah. And for 4, actually what you're going to realize is, let's say you do have 4 rows. And if you want a valid solution here, you can try this. I'd encourage you to try this. We can actually even have 4. We can actually have 4 rows here. It would make it even easier. But it doesn't work for 4 rows, so it wouldn't work for 5 rows. But you can try it if you want to. Actually, I guess we can't have 5 rows, sure. Okay. So what we're actually going to try to do is we're going to try to draw a 4 solution. Now, what we also want to try to draw is we're going to try to draw a 4 solution where a 2 solution does not work. So we're going to try to kind of even out the ones if we can. So let's say we put some ones here. And remember, for a 4, we can have maximum of 2 ones at every single column. Put some ones here, maybe. Put some ones here. Put some ones here. And now we want to look at, okay, so from what we did, what rows have a 2 solution? Well, this row and this row have a 2 solution for now, right? What else has a 2 solution? Well, this row and this row has a 2 solution. Also, this row and this row has a 2 solution. And I'll show you what I mean by the 2 solutions. Okay, so let's fill in these zeros. So what I mean by the 2 solutions is, so far, if we take this row and this row, you could see that there would be a 2 solution here, right? Because if I use these 2 rows so far, at each column, there's only 1, 1 maximum. So there's 0, 1, 1, 1, which would give you a 2 solution, a 2-row solution. And the same thing for this row and this row, right? So this one, right, and this one is, you can see that, you know, there's a 1 and a 0, 1 and a 0, 1 and a 0. And so that would also be 1 maximum, and so on. So no matter, you can try this if you want to, but no matter how you put in these numbers, if you put in the numbers in a way where a 4-row solution is possible, fine. So like there's so many that are still a solution, no matter how we put in the rest of them. Like, let's say we just put them in here. There's still going to be a 2-row solution somewhere. And you could see that actually there is a 2-row solution. So this is a 2-row solution right here still, right? So this row and this row is a 2-row solution. And is there anything else? Yeah. So also this row and this row is a 2-row solution, and so on. And so you can try this, but it definitely is quite difficult to, I think this is the hard part of this problem. It's quite difficult to understand like that's the case. But for any row equals 4, in order for this to be true, there has to be a 2-row solution. No matter how you put these ones, you can try it all you want. If you put in the ones in a way where there is a 4-row solution, there will automatically always be a 2-row solution. And so now that we can simplify that, we don't need a 5, we don't need a 3, we don't need a 7. And then for 6, it would be the same thing. If there's a 6-row solution, there's going to be a solution with less rows automatically. You can try that as well. And so now that we simplified that to... So now the only rows we need are rows equals 1 and rows equals 2. And so we simplified that, right? So now we need to figure out how do we do this and how do we do this in an efficient way? Well, let's think about, first of all, how would we even get these solutions? So for row equals 1, it would be pretty straightforward. We can go through the rows and we can just check, okay, is there a row with all zeros? If there is a row with all zeros, then that's a valid subset, right? So that would be pretty easy, and that would be big O of n time. Okay, but what about for row equals 2? So for row equals 2, we'd actually have to compare every row, right? We'd have to compare row I to row j. We'd have to compare every single row until we get a solution. And then we'd also have to compare every single number in the column to make sure there's only 1 1 in each one of them. And so what would be the complexity of that? Well, that would be row times, let's say this is the number of columns. So let's call that C. Now, the nice thing about this, and this is kind of actually from doing these hard biweekly problems, you're going to see this happen a lot. You're always going to get constraints, not always, but most of the time. You're going to get constraints where 1 is really big, right? So number of rows is 10 to the 4th, but number of columns is only 5. And so this doesn't cost you much. So you're going to want to try to optimize your solution to where you're not doing this in n squared, but it's okay to have column squared or columns cubed or whatever. In this case, we don't need that, but that's just something you want to look for, is you want to look at the constraints and you want to figure out roughly what's okay to have a quadratic solution for and what's not. What do I definitely need a linear solution for? And then, so this would be the linear for this. We need to figure out a way to simplify this. And so how do we simplify this? Well, so we can actually use our columns. So if we can only have 5 columns max, let's think about it. So we have 5 numbers, right? Let's just say we have some numbers in each row. Well, what's a better way of comparing these numbers? And first of all, let's start thinking about how many total different combinations can we have, right? So we have 5 numbers maximum. How many combinations is this? Well, if you think about it, this is just binary, right? So this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, right? So this is 2, 4, 6, 8. Did I do that right? No, I did not. So it's 2, 4, 8, 16. Okay. So there's actually 16 total numbers we can represent, I believe. Or 15 technically, right? Let me see, actually, hold on. So 2, 4, 8. So it's actually, sorry. It's not 16, it's 32 numbers, right? Because if this is a 1, this is 16. If this is a 1, this is 8. This is 4. This is 2. And this is 1. So this would be the sum of all that, which would be 31. But this can also be a 0. So we can represent 32 numbers. So each row can only be 1 through 32. And so instead of comparing row by row by row by row by row, what we can actually do is we can just get the binary representation of the row. We just get some number and then we store the index, right? And so then we traverse the rows. So now it's going to look like we just traverse the rows. For every row we traverse the column. So that's going to be linear time because C is only 5. So that's just going to be row complexity. And there can only be 32 numbers max. Then we can just have a dictionary. And then for every single number, so let's just call that num, we store the row index. And then how do we know if 2 rows are a subset? Well, it's pretty straightforward actually. So let's make this bigger again. So how do we know if 2 rows are a subset? Well, let's just say we have some numbers, right? We have some numbers and we have something like this. Let's just say we have something like this. How do we know? Remember, for a 2 row, the most ones you can have in a column is 1. And so you're either going to have, these are the only combinations you can have in a column for this to be valid. So you can either have 0, 0, 0, 1, or 1, 0, right? Those are the only combinations you can have. Well, what's a way to check if these are the only combinations you can have? Well, it's pretty easy, right? You just AND. So if we AND our 2 rows, like we get some number here, we get some number here, and we AND them, if we have a valid subset, then our result will be 0. Right? Because we can only have 1, 1 in each column maximum. So an AND with a 1 and a 0 is 0. An AND with a 0 with a 0 is 0. An AND with a 0 with a 1 is 1 or 0. And the only thing that gives you an AND of 1 is a 1 and a 1. But if we have a 1 and a 1, then we don't have a valid solution, right? Like if this is a 1 and this is a 1, then we don't have a valid solution because we can only have 1, 1 maximum. And so what we're actually going to do is we're going to go through our rows and we are going to store the integer result and an index. And then it's pretty straightforward. Instead of comparing row to row, if we can only have 32 max, we can just traverse, like let's say we know how many columns we have. So we have some columns and we get some like max number. Let's say we have 5 columns here. So we know our max number is 32. What we can actually do is we can just traverse every number from 0 to 32 and then compare it to every other number from 0 to 32. And we just always check, is that number in our dictionary, right? So first thing we would like look for a 0, and then we'd see, okay, is there something with index 0 in a dictionary? Yes, there is. Let's say, okay, well 0 is actually going to be the 1 row solution, right? That's just 5 zeros. So if we do get a 0, we can return straight away. But let's say we don't get a 0. Let's say we get a number like 2, right? So what would 2 look like? So 2 would be this. Then we just compare 2 to every single other number. And then for every other number, it only goes up to 32. We can just AND it, right? So we do 2 AND numbers 0 to 32. And then if we get a 0, then we just say, okay, then if that's the case, we stored. So when we're comparing it to other numbers, first of all, we're just going to say like, okay, is this number in our dictionary of rows? Where do we actually have a row with this number? If not, we can skip. But otherwise, we AND them, and then if it is 0, then we just know where we had a 2 and where we had whatever other number. And so now what's our time complexity? So our time complexity is actually 32 by 32 for these comparisons, which is, way less than 10 to the 4th times 10 to the 4th. And so our total complexity is going to be, we need to go through our rows, right? And so that's going to be 10 to the 4th times column. And then when we're actually comparing 2 rows to make sure that they are a valid return, it's actually only going to be 32 by 32. And so our time complexity here, this would be way bigger. So our time complexity would be O of number of rows. And remember, columns is only 5. And now we have a linear solution. So hopefully that makes sense. And yeah, honestly, the toughest part of this problem is to realize that for these good subsets, you only need actually subsets of 2 rows or 1 row. You're never going to have an odd number because an odd number is strictly worse than even. It doesn't give you anything. And any number bigger than 2, if that is valid, then something smaller will also be valid. So we can just check for the smaller stuff. Okay, so let's try to code this up, see how it goes. So first, remember, we're going to we need a dictionary for like the numbers in each row. So how do we want to do that? Well, we can just do, let's see what we're going to call this actually. So we can just call this numbers maybe even. Okay, and now we want to go row by row and compute the binary representation of the row, right, in the number. So like here, this would be 6 and so on. So we need to do that. And so we need to actually do an enumerate, I think, or we need to go, we also need the index of the row. And by the way, it's okay if we get the same number twice. Like if we get 32 and that's at index, 5 and then it's at index 100 or whatever, we only need one of them. So actually, do we need one of them? Yeah, we only need one of them because if you get the same number twice, that number ANDed with itself will never be 0, right? Because if you get a number like this and you AND it with it yourself, this is never going to be 0. This is going to be a number ANDed with itself will just be that number again. So we don't need to store the address of the same number multiple times, or we can just overwrite it. Like either one's fine. So it doesn't really matter. Like we don't need to store a list or anything for a dictionary. We just need to store a number and then one index where it's at. Okay. So now we need to do for iv in enumerate here. This is going to be grid. So the index is going to be the index of the row, and then the v is going to be the actual row. Now I probably do want to get like the number of columns and rows. Maybe we'll use that, maybe we won't. So let's just do that. Equals length grid 0. Okay, so now that we have that, what we actually need to do is we need to go through the entire row, and then we need to get like a total number. So let's do that. So let's just say we get a total here. Okay. And then we get maybe a power of 2 or something. Sure. And so that's going to start at 0. And then we need to go through the entire row, but we need to probably go through it backwards, right? So like this will be 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so on. And so we need to go through, and V, so remember, V is our row here, so we can actually just write like row. Okay, and so this is going to be, we need to go through the values backwards. So for value in rows, so this is actually going to be a row, but we need to go backwards. So I think I can do something like this. Yeah. So then we just do total plus equals value times, let me think here. So this is the power of 2, right? So this would actually be value times 2 to the power of 2 here. Yeah, because like this is 2 to the 0, then it would be 2 to the 1, and so on. And value is just if it's 0 or 1. So there we go. Now we need to increase our power of 2 here. Okay. So now that we get our total, now what we need to do is we need to actually store that. So we need to store this like total value, and we need to store the index. So let's do that. So we're going to put that here. And this is going to be numbers of total equals I. Okay, and I think that should be that. So let's just print numbers just to see if we did that right. That should be right. It's kind of early in the day, so I'm a little tired and doing some stupid stuff. So let's take a look. So we have 6 at index 0, which is correct. We have 1 at index 1, which is correct. And we have 15 at index 2. Yep. Okay, so perfect. So that's exactly what we want. So we don't even, honestly, we don't even need to, like, for the next part, we don't even need to see how long our column is and figure out what values we can compare. Because comparing 32 to 32 is just so cheap in terms of time, right? Like, let's say we only had one column, technically, yeah, we'd only have to compare like 1 to 1 or something. But it's totally fine to just do a 32 by 32 anyway, because it's only 900 operations. This is going to be like way more than that. So, okay. So now we have to go through all our numbers and compare them, right? And so we have to compare every number from 0 to 31. So that's going to be, and we have to compare that number to every other number from 0 to 31. So let's do that. So for I in range, this is going to be 32. Yeah, so 0 to 31. For j in range, 32. Okay. So we can make this a little bit smaller, but that's fine. So if I in numbers, so if the number isn't even in there, we don't even need to do that, but we can do this. For j in range 32, and then this would also be if j in numbers, right? So if the number isn't even in there, then we don't have to do anything. Actually, so yeah, if j in numbers. Okay, so now this is where we need to do the and we need to compare. So first of all, we can check for the I solution. So we can do that right here. So if I equals 0, then we have that 0 solution, right, where we have the one row of all zeros. So we can return here. So we can just return numbers I. So that should be this kind of solution. Okay. Now for j. And technically, we don't have to compare number to itself. In fact, we probably don't want to, but it doesn't really matter, like I said, because if we compare the number to itself, the and will never be 0, so that's totally fine. Okay, so if this is right here, yeah. So if I and j, oh, we don't need this, equals 0. So that means we have the 2 solution, I believe. right? Where if you and the numbers, this is the two-row solution. Now we need to get the indices of the two rows, and then we need to return them in ascending order, I believe. So let's do that. So let's just say res equals nums I, nums j. And then we need to return them in ascending order, so we can just take these two numbers, and if j is greater, we can swap them. So if nums j is greater than, or less than, right? Yeah, nums I. Yeah, res equals, swap them around. So that part is pretty straightforward. Okay, now we just return res here. Otherwise, if we went through this whole loop and didn't find anything, we just return the empty array. So let's see if we did it right. Dumps. Let's see here. Nums. Okay, so it should be numbers. Okay. See what else I screwed up. Okay. Nice. Okay. Let's actually see. Let me check one more time how we actually did compared to other people. But yeah, you can definitely make this a little bit simplified, but as far as time and space complexity, like it's not going to be the way you would simplify is, yeah, you could make this, instead of do a 32 by 32, you can make it less, and that would run a lot faster for something that didn't have a lot of rows. But let's actually maybe do that. So how do we do this really quickly? I'm curious. So let's see. So this would be, let's see what we'd have to compare. I think it would be 2 to the columns, right? So if columns here is 5, 2 to the 5th is 32. Yeah, so I think this is 2 to the columns, actually. I guess we could do it. Whatever, it's fine. See if that runs any faster. But theoretically, runs like space-time and stuff, it wouldn't. No, it's the same. Okay, whatever. Okay, so anyway. So that is a valid solution. Now let's think of the time and space. Yeah. Okay. Yeah, I think you could actually make this even simpler, but once again, I don't think it would make it, like what you could do is you could do something like this, I think, as well, technically. So let's see. Yeah, but I don't think this will make it any faster either. Yeah, it's the same. Okay, because I think it's probably something in here that, let's actually think about, yeah, so let's actually think about making it a little faster. So instead of doing this row reverse thing, let's not do that. Let's just traverse backwards, because I do think this might get quite expensive, because we are creating like a new element every time. And let's just iterate it instead. So for I in range, I don't want I want j in range, length. So what do we want here? We want row, but we want to go backwards. So this is just, let's just do this. Okay, and now, so I don't think we want value here, right? We want row j. Okay, let's see if that's still right. Oh, we also don't need this print numbers. Okay. Let's see how that goes. No, it's still the same. Interesting. Okay. Okay, so anyway, let's just do the time and space here. Yeah, I am curious. This is a new problem, so maybe there's like something a little more efficient, but it's hard to say, honestly. So, okay. Anyway, let us go through the time and space. So time, so we go through the rows, and we are going through the column for each row, and then we're doing this like total thing, which is fine. And so that's going to be however many rows this is. So this is going to be of rows, and then column should only be up to 5, so that's just constant. So that's that for time. And now for space. So we did have a dictionary, but the dictionary, like I said, can only hold 32 numbers. So that should be O of 1, actually. Yeah, the dictionary can only hold 32 numbers, so that should be O of 1. And then this should be, we're not making anything extra here. So we do have our output array, but that's only 2 elements. Yeah, so I think space is O of 1 and time is O of rows, and that should be right. Okay, so that's all for this problem. Hopefully you liked it, and if you did, please like the video and subscribe to the channel. Thanks for watching, and I'll see you in the next one.